So, one of the main things that I get asked about a lot, or certainly have done in the Discord server from time to time, is about the player controller that we're using in SquareOff. If you don't know what SquareOff is a game that we're currently working on. It's got a Steam page. I would love it if you could go and give it a wish list, and I would also love if you tried out the demo. There's a link in the description to get access to both of those things. So, something that I've done with SquareOff is the key focus of the game was to have this fun physics-based battle arena, and for that obviously the player controller is a very important component. So in this video I'm going to be walking you through the process of how I went about creating the player controller that we're using in SquareOff. Let's go! Hey guys, welcome back. It has been a little bit of a while. I feel like it's not been any longer than usual, but I might be completely wrong with that. But look! We've got a new studio, effectively, kind of, a little bit. We've got new lights, we've moved the desk, I'm still in the same room, but it's, you know, it's much nicer. We've got my speakers set back up again, nice backlights, we've got proper microphone, proper lighting, so I'm planning on doing a lot more of these kind of videos moving forward. As I said though, before I take any more time waffling about random stuff, today we're going to be looking at SquareOff, specifically the character controller and the way that I've gone about programming how players actually play the game and the thing that you're moving about with. The player controller and the way it works is split into two distinct parts. We have the controller 2D thing, which is what is responsible for handling our collision detection and the actual movement of our physics object. And then we've got the player controller class, which is responsible for taking the input, calculating our physics, and handling all of that, passing it through to the controller component and allowing things to move. So with that in mind, let's jump into Unity and take a look at our first script, the 2D controller. So over in Visual Studio, I've popped open the scripts and you'll be able to see them on screen now. We have the controller 2D open, which is a very basic class and is taken pretty much primarily and almost completely from Sebastian Laig's Unity 5 platformer controller tutorial. For those of you who've been around since the beginning of the channel, you'll probably know that I reference this controller a lot when working on 2D games, as I mentioned it in the first video that we ever published on the channel. As in that video, I highly recommend you go and check Sebastian out. He's doing a series called Code Adventures at the moment, which is probably my favourite series that he's created, and it's really interesting for people who are into the more experimental kind of back-end Unity type stuff, so definitely check him out. So to break this script down, first things first, on line 5 we have a require component tag, which just ensures that our controller has to have a box collider 2D on it. The reason for this is that we're using a square shape to figure out where our collisions are going to be done, both in the up, down, left and right directions, and it makes a lot more sense to use a square shape for this kind of thing rather than a circle or anything like that. Moving on to the parameters, we have a parameter for the skin width. This is effectively, as it says, how thick the skin of our character is going to be. If we think about the fact that we're going to be using raycasts in this character controller, we need to have some kind of accountability for where the inner edge of our character is, so that we can still be casting raycasts and hitting something even when we're touching a surface. In most cases, if we went directly from the edge of a square while the square is also touching a surface, that raycast is going to go straight through the surface that we're sitting on top of, so we want to make sure that we're accounting for that difference in space using something like the skin width. Next up we have a layer mask. This is simply the environment mask. It is the thing that we want to collide with. We set this in the Unity editor. For me, I'm specifically just using the floor. We don't want to collide with players because that's just not what I was going for in this game. Collision info is a custom data type that we've made. Let's go take a look at that. Really simply, it is a little struct with a set of booleans for if we've got a collision detected above, below, to the left or to the right. We've also got an integer representing the direction that the player is facing in, 1 for right and -1 for left. And then we've got a public void reset, which is used for setting all of our collision info to false, basically resetting the collision info. Back up to the top, the final two things we have are a reference to our box collider, which we are calling col, and a reference to our 2D rigid body, which we're calling RB. Now, I want to just take a little quick interjection right now to talk about the fact that I could be doing all of this with Unity's default physics alone, just using a rigid body, and to some extent we kind of are. But as you'll see when we move through into the player controller script, there's actually a little bit more going on where I'm doing some custom physics calculations, accounting for a better gravity curve, and some improved jumping logic that just help make things a bit easier and feel a little bit better. But we're using Unity's default rigid body for actually applying those velocities and applying those forces so that we get some easier application of motion. With regards to functions, the controller 2D is pretty simple. We have a function called move. This simply takes in a vector 2 for the velocity that we want to move the controller by. We reset our collision info. And then first things first, we want to do a check to see if we've got some velocity in the x direction. If we do, we're going to set the face direction of our collision info to be in the direction of that velocity. We then make sure that we do a check for horizontal collisions. We check to see if our velocity on the y-axis is not equal to 0, and if so, we'll do some vertical collisions there. Finally, we update the velocity of our rigid body with the velocity that we've calculated finally. Some of you who are new to C# code might be wondering where I've actually done any editing to the velocity parameter here. Well, if you look at these references that we've got for our methods for horizontal and vertical collisions, we're passing in velocity with this ref keyword in front. What the ref keyword means is that we're passing in this parameter by reference, and effectively what this does is give it direct access to the original parameter that we were using. So rather than just using it in calculations, any changes that we make to it in this method will be applied to the original parameter as well. With that in mind, let's look at our horizontal and vertical collision methods. These ones are relatively simple, and as you can probably guess, they handle the collisions for the horizontal and vertical axes. As discussed previously, we pass in a reference to our vector2 velocity. We're then going to create two float variables. We've got one for direction x, representing the direction in which the player is moving, and cast distance, which is how far we want to fire our raycast. I've had trouble finding the word there. So we calculate that cast distance by doing the absolute value of the velocity. mathf.abs is a default function in Unity for returning the absolute value of a given float or integer. The absolute value is simply the value that that integer or float holds minus the sign. So if we passed in -1, we would get an absolute value of 1. We then add the skin width to this for the reason that I mentioned before. We want to make sure we're accounting for the fact that the player could be directly on ground, and if we were to cast from the edge, we would end up with the raycast going straight through the surface that we want to touch. Next thing we do is a quick check to make sure that our velocity is greater than the skin width. If not, we set our cast distance equal to double the skin width. Next up, we're actually performing the 2D raycast. We store this in a variable called hit of type raycast hit 2D. This is a simple box cast where we use the transform's position as the origin, the transform's scale minus the skin width as the size, an angle of 0, and in the direction of direction x multiplied by vector2.right. We go over the distance of cast distance, and we are using the environment mask as our layer mask for what this is actually detecting. Finally, if we hit something, first of all, I'm doing a quick debug.log to print out the name of that transform just for debugging purposes. We then update the x value of the velocity to be equal to the hit distance minus the skin width, all multiplied by the direction that we're facing in. Finally, we will update our collision info based on whether our direction is equal to -1 or equal to +1. The logic is much the same for the vertical collisions, with the difference being that we are working on the vertical axis. So rather than using our x velocity, we are using the sign of velocity.x, similar to abs, except instead of returning the value, we return the sign bit. So if we passed in 5, we'd get a result of 1. If we passed in -10, we'd get a result of -1. And that's basically everything for our controller 2D. So now that we've covered that, let's move on to looking at the more complex script and the thing that we actually use for this stage, which is our player movement script. So hopping over to the player movement script, things are a lot more bulky. The reason for this is because we were using this code in prototypes, and generally in prototype code things tend to get a little bit more messy and a little bit less managed. So we've got a lot of functionality existing in here which we probably wouldn't want to have in this class as we're moving forwards. For the purposes of this video, I'm just going to be covering the logic that handles the movement of the player and not things like how we're taking damage or how we're collecting power-ups. We'll cover those things in other videos if people are interested. So first things first, we've got a reference to our rigid body, and we've also got a reference for which layer the ground is on. We also need to make sure that we've got a reference to our player input module. And finally, we've got a private boolean frozen, which I use for checking to see if objects in the scene should be frozen and able to move. Scrolling down, we've got a section for the movement parameters. This contains what you'd expect there to be, like the move speed and the jump height. We've also got a couple of parameters for controlling how the smoothing works when on the ground and in the air. Smoothing is a float that we apply to the movement to make things feel a little less stiff. It's the difference between pressing the right stick and suddenly you move instantly right with no delay, and pressing the right stick and slowly speeding up as you move to the right. Finally, we have some internal data which is used for tracking some of the things we're allowed to do. This includes a reference to our velocity, what our jump velocity would be, how long it takes to reach the peak of our jump, and an input vector. We've also got some things for assessing whether we can jump and whether we can shoot. These are the grounded variable and in-air last update variable. Finally, we have some reference variables called spin smooth ref and velocity smooth ref. These are a little bit more complex, but we'll talk more about them when we get to the point in the code where they're supposed to be used. So first things first, let's talk about the initialization of some of these components that we've got. The most important one that we're probably going to be looking at is this calculate jump velocity, which is called in the init method. Again, I won't go into too much detail about how this init method is called. That's more to do with the way that I'm handling the new input system with multiple players. For calculating jump velocity, this again is code that is given by Sebastian Lage. We are doing some simple physics to work out what the time to our jump apex is based on the jump height and the value of gravity in our physics 2D settings in the Unity project. And we're then using that value to calculate what our jump velocity will be. First things first, we check to make sure that the player is not frozen, because if we're frozen, we don't want to be able to do anything. Secondly, we will check to make sure that we've actually got a player input. If the player input is null, obviously we can't take any input from anywhere, and doing this kind of thing will throw some null pointers with the calls that we're making further down the if statement. So then we have a series of checks for what the input is going to be. We simply set our input vector equal to the move input from our player input actions. We do a check to see if the player has attacked, followed by if the player has pressed the jump button, and finally if the player has pressed the use button, which is used for triggering special items and power-ups. Otherwise, if we are frozen, we just set our input vector to vector2.0. Now we need to move into the fixed update. The reason why we've got these things separate in the update function for the input handling and then the fixed update function for the actual physics and controlling of that movement is because when messing with physics, if you perform these things in the update method, you can have some weird things happen, some weird artifacts, missed collisions and stuff, just because of differences in frame rate. When we use fixed update, it keeps it on a fixed time scale regardless of frame rate, and so you end up with consistent and predictable collision behavior in any environment. We want to keep the input handling in the update method, however, because we don't want the player to press a square button in between updates and suddenly the input gets missed out. So that does need to be dependent on the frame rate, as it will be reactive based on what the player is seeing. So first things first, in our fixed update, we are calculating what our smooth time should be. As I mentioned before, this is how much we are smoothing the movement input based on whether you're on the ground or in the air. So we do a simple inline if statement, as I like to call them. It's also known as a binary operator, where we say, are we grounded? If we are, we'll use the grounded smooth time. Otherwise, we'll use the aerial smooth time. Next thing we do is check to see if we are knocked back. The player gets knocked back in this game if they take any damage, and that knockback becomes greater and greater depending on how many times you've been hit in a certain round. If we are knocked back, I want the smooth time to be a little bit lower, so we're using 0.5 multiplied by the knockback percentage plus 1. The higher the smooth time gets, the longer it takes for you to reach the velocity you want to be at, and so if you've got more knockback, it's going to be harder for you to bring yourself back onto the screen. We're also doing some updates for time to recovery and certain particle effects that we're instantiating, but that's not important for the movement handling in this system. Next up, we're doing a check for our angular velocity. One of the things that I really wanted to do when I was designing this character controller is have it that when players jump, they do a little spin, because just having a square go up and down is kind of boring. So I wanted to make that a little bit more interesting and a little bit more interactive. So the angular velocity of the rigid body is what we're using to achieve that effect. If our angular velocity is not equal to 0, then we want to slowly move our angular velocity from what it currently is down to 0, making a reference to that spin smooth time ref, and then passing in smooth time as the parameter that we're using for controlling that. This is the instance where that ref spin smooth ref is used. Much like we saw before, we're passing in a value by reference, which means it's being altered by the method and that value is being returned back and stored in the original variable. This is just a requirement of the smooth damp method in the mathf class. Don't need to read too much into it, just know that it works like that. Next up, we are setting our x velocity. We're doing this using the mathf.smoothDamp so that we can account for some smoothing between the different things. We're going to be smoothing from the current velocity on the x-axis to our x input multiplied by the move speed. Again, we're passing through this reference for velocity smoothing, and the smooth time is the amount of time that we want to smooth over. We're setting the y velocity based on the rigid body's y velocity, nice and simple. And then we just set the velocity of the rigid body equal to our velocity. So that's everything for the actual movement process. The final thing left is making the player jump, which is handled in its own method called when we press the jump button on our keyboard or PlayStation controller, for example. First things first, we have a trigger jump function, which is called when we actually press the jump button. This simply does a check to see if we're grounded, and if so, we can jump. Otherwise, the design of the game that I chose is that I wanted players to shoot when they're in the air and they press the jump button again, much like in Downwell with the jump boots. So we do a check to see if the ammo count is greater than 0, and if we're allowed to shoot, we will do a little jump and then actually perform some kind of shooting. As for the jump method itself, we are simply using a private void where we pass in a float for the multiplier, which defaults to a value of 1. In this method, first of all, we set our rigid body's velocity equal to a new vector2 with an x value equal to the original x velocity of our rigid body and a y value equal to the jump velocity multiplied by our multiplier variable. After this, we're doing the calculations for that rotation effect that I was talking about earlier. First things first, we figure out the direction we want to rotate in. This is based on what our x velocity is. If the x velocity is equal to 0, we're going to use a random number between -1 and +1. Otherwise, we just use our negative x velocity. We're then adding that rotation using the rigidbody.addTorque method, passing in a value of 5, which is just kind of a value I picked out the air and ended up feeling right, multiplied by the sine of our rotation direction, and multiplying that again by our multiplier using the force mode of impulse. Finally, we do a check to see if we're grounded. If we are, we're going to play a sound effect to signify that we've jumped and instantiate a particle effect for that jump effect. Putting all those pieces together, we end up with a player controller that looks something like what's on the screen at the moment. And it's really kind of that simple. It's not too complicated. If you take some time to read the code and break things down a little bit, the steps are actually quite simple. It looks complicated in the instance that we have here, simply because of all of the other systems that are bloating out that class and should be moved into a separate one. Hopefully you enjoyed that video. If you're interested in seeing more of the code and seeing more videos like this, please consider subscribing to the channel, as I'll be uploading much more videos like this moving forwards. If you're interested in getting access to this class after the video, consider signing up to our Patreon page below. You will also get access to live streams after they've happened, along with some early access to video games that we release in the studio. Final thing, if you want to get involved with some of our community and the cool developers that we end up talking to and working with, consider joining our Discord server and getting chatting and showing off what you're working on. Been a real pleasure bringing videos back. Hopefully I have more to come soon, and until the next one, cheers guys.